JFET, SIT, MOSFET, triode versus pentode perspective. To understand why the V-FET, the static induction transistor, was such a special device, it is helpful to begin with a much more common component: the JFET. A JFET is a depletion-mode semiconductor. This means it conducts by default, and the gate voltage does not turn it on, but instead restricts the current flowing through the channel. The gate is not isolated by an oxide layer. It is a PN junction. As the gate voltage becomes more negative, the depletion region gradually expands into the channel, and the current decreases continuously and in an analog manner. There is no sharp threshold voltage. There is no digital on-off switching. This is a purely analog control process. If we examine the IDVDS characteristics of a JFET, we can see that the curves do not flatten completely. There is no hard saturation region. The drain current still depends on the drain voltage, resulting in behavior that is very similar to that of vacuum tube triodes. This is why we often say that a JFET exhibits a triode-like characteristic. And this is exactly the point where the static induction transistor becomes easy to understand. A SIT operates on the same fundamental principle as a JFET, a PN junction gate, depletion mode operation, and current control by restriction rather than switching. The difference is not the principle, it is the scale. A SIT uses a vertical, deep channel structure, allowing operation at much higher voltages and currents. For this reason, it is technically correct to say that a SIT is essentially a power JFET. This also explains why the conduction curves of a SIT closely resemble those of a JFET, just over a much wider voltage and current range. Both behave in a triode-like manner. Both provide continuous regulation, and neither is a switching device. Here, however, we reach an important difference. When compared to vacuum tubes, a triode, regardless of how triode-like its curves may be, is not a complementary device in the semiconductor sense. There is no simple N-type and P-type pair that can be mirrored to form a push-pull output stage. A SIT, on the other hand, is a semiconductor. It existed in both N-channel and P-channel versions, making true complementary pairs possible. And this is where the technology became both brilliant and tragic at the same time. Manufacturing P-channel SITs was extremely difficult, the production yield was very poor, and the process ultimately became economically unsustainable. Short detour: MOSFET, pentode-like behavior. The MOSFET is based on a completely different philosophy. Here, the gate controls the channel through an insulated oxide layer, and operation is defined by a well-defined threshold voltage. In MOSFET IDVDS characteristics, a hard saturation region appears, where the drain current depends only weakly on the drain voltage. This behavior is much more pentode-like. The current is primarily determined by the gate, while the output voltage is largely decoupled. This makes MOSFETs excellent for switch mode operation, digital logic, and high-efficiency power electronics, but not triode-like in character. Conclusion: JFETs and SITs do not aim to switch. They aim to regulate. They behave like a voltage-controlled variable resistor, or a potentiometer, with the crucial difference that there is no mechanical contact, no wear, and no contact noise. The regulation is performed purely by voltage, fully contactless. This is what gives these devices their triode-like character. And this is also why they were so special in audio applications. Even though, on an industrial scale, they could not compete with MOSFET technology.